Everybody, I wanted to solve this example because it's going to give us a little bit of insight on how we should take care of problem 2 on homework 5. It says that I've loaded a block into a spring launcher with a known spring constant, and it's going to push itself out the end. I want to know how far it has to compress to have a final speed of 3 meters per second. But the big wrinkle is that there's friction that's going to do negative work in this situation and kind of slow the block down as it goes. So we're going to have to compress a little further than we would without friction to get the same speed. So to figure this out, I want to first draw down a free body diagram that shows the forces that are acting on this object. There's a spring force, I'll call that F big S, and then there's a friction force, which I'll write as lowercase f sub k. I know what the spring force is at any given position, and therefore I also know that the work done by the spring is just 1/2 k delta S quantity squared. And we did that in class on Wednesday. The work done by friction is a little trickier. It's equal to the magnitude of the friction force, magnitude Fk, now I'll draw an arrow to indicate the magnitude of the vector, times the magnitude of the displacement vector times the cosine of the angle between them. And because the displacement is forward and the friction force is acting backwards, the angle, that should be an arrow, the angle between them is 180 degrees. So the cosine of 180 is -1, and we also know that the friction force has magnitude, in this case, of mu k mg. Therefore, this whole term has value of negative mu k mg times delta S times the cosine, no cosine. The negative is taking care of the cosine term. Okay, so now let's go ahead and plug this all into the work-energy theorem, which says the work done by the spring plus the work done by the friction is going to be equal to the change in kinetic energy, and that's going to be equal to 1/2 mv final squared, and we'll assume it starts at rest, so that's -0. And from there, we're going to go ahead and say, all right, so if this is 1/2 mv squared, I can write down my other two terms. I'm going to say that 1/2 k delta S squared minus mu k mg. Oh, I knew I was forgetting something. No, I'm not. All right, we're all good. Not crazy. Is equal to 1/2 mv final squared. Or I can pull this minus 1/2 mv final squared over to the other side, which leads to a very suspicious looking kind of bundle of math. And the reason why I call it suspicious is that the first term has that delta S squared in it. The second term has this delta S here. And then I'm writing down a term without that delta S. And we have to solve for it. So this is a quadratic formula. And that means that I can solve it by using the quadratic formula, which says that if this is if this is B, to be clear, everything in front of but not including the delta S is the coefficient in front of it. The 1/2 k is the coefficient in front of there, and then minus 1/2 mv final squared is that coefficient. So in the quadratic formula, that's A, that's B, and that's C. And then I can write down negative B. This is the solution. So delta S equals negative B, mu k mg, plus or minus the square root of b squared, which is mu k mg, minus 4 times A, which is 1/2 k, times C, which is minus 1/2 mv squared, or v final squared. Okay, that's good. All over 2a, and so that's 2 times 1/2 k, or k. Now what I'm going to do is I'm going to multiply the 2 times a half and give me a 1, and I have a k. I'm going to go ahead and stick that k under this first term. So this is equal to minus mu k mg all over k plus or minus the square root of, and then if I put the k in the radical, it has to be squared. Oops, speaking of squared, this should be squared here. All right. And then we bring in the radical squared, and I get the same thing, mu k over mg, mu k mg over k quantity squared, mu k mg over k quantity squared, muddling to the future. 4 times a half times a negative half, or is going to be a plus 1 times k mv final, mv final squared, all over k squared. Okay, and this is getting simpler, believe it or not. And I'm going to pull down here and say that delta S, give me some room, is equal to mu k mg over k plus or minus square root of mu k mg all over k squared plus k, mv final squared over k. Radical, and I can then do my variable substitutions. So I get what mu k is 0.2 times m, which is 1 kilogram, times g, when this problem is 10 meters per second squared, all over k, which is given as 50 newtons per meter, plus or minus square root of ms. So that's the same term squared here. So that's 0.2 squared times 1 kilogram squared times 10 meters per second, quantity squared, all over 50 newtons per meter squared, plus, let's see here, m, which is 1 kilogram. V final is 3.0 meters per second squared. K here is 50 newtons per meter. And then we go to our calculator, tap, 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 grind, grind, grind. And I got, when I tried this, 0.46 meters, void where prohibited by law.